Hello everyone. So in this video, we're gonna cover electricity for honors physics. So it is not for AP. So this is honors physics. It's because the Rosenwald honors physics class have the electricity exam, and it was said it would be circuits, but you don't actually know if it's both circuits and electrostatics. So I'll cover the entire unit just to be safe. So sorry, this is like late for the video, but I came from like a vacation, so sorry for it being a bit late. So first we're going to cover charge. So what is charge? So charge is an inherent property of matter. So like mass is a property of matter, charge is also a property of matter. The charge can be positive or negative, and objects can have an electrical charge, either being positively charged or negatively charged, or it can be electrically neutral. The unit of charge is the coulomb. So the law of conservation of charge states that charge cannot be created or destroyed, but can be transferred. When two charged objects touch, they will distribute themselves equally on the objects. So suppose you have two identical charged spheres, one with positive 20 microcoulombs. So this little symbol here, it's micro, which means a millionth of a coulomb. So positive 20 microcoulombs, and the other would charge negative 32 microcoulombs, and you touch them together. So what will be the resulting charge on each of the spheres after they touch? So what you want to do is you want to find the total charge Q. That's the net charge. So the total net charge, so you have a negative charge and a positive charge. You have positive 20 microcoulombs of charge, but you also have a negative 32 microcoulombs of charge. So if you want to find the total charge Q, what you should do is you just add them together and you'll get negative 12 microcoulombs. So when they touch the negative charge, the electrons, which carry negative charge, they will all distribute themselves equally until they're all in equilibrium, until no electrons don't want to move any further. So that's when the charge is the same. So since it's being distributed among two spheres, you just divide this net charge by 2 and you'll find a total, not total, but the charge in each of the spheres will be negative 6 microcoulombs. So what are these electrons? And what are protons and neutrons? So you might know protons are about 1,000 times more massive than electrons. And I've given the masses right here. So the mass of proton is 1.67 times 10 to the negative 27 kilograms. And the electron mass is a lot smaller. It's 9.11 times 10 to the negative 31 kilograms. Excuse me. But both of these particles have the same magnitude of charge, but with opposite signs. So that magnitude will have a value of about 1.6 times 10 to the negative 19 coulombs. Now neutrons have zero net charge. So, and anything that's electrically neutral. So neutrons don't carry a charge. And the little things that make up the neutron that make up that charge, they will balance out. So it doesn't really have zero charge. Charge is just a property of all matter, but it will have zero net charge. So the positives and the negatives balance out. So, and the proton and the electron, well, the electron is the fundamental charge carrier, so you can't really have anything smaller than this charge by itself, and you can't really have like halves of these charges by common sense, so you can't really have one and a half times this charge, because you really cannot have half an electron. So they must be integer multiples of this number. This is known as the elementary charge, the basic electron charge. It's the smallest charge an object can have. So here are the methods of actually generating charge. By generating, I mean like giving a charge to an object, not actually creating charge, because that violates conservation of charge. But generating, you mean like a transfer, giving an object a charge by transferring it from one object to another by 3 various ways. I included the diagrams. So first, you might have read here is charging. Oh, I'm sorry. So charging by friction. So basically, what happens when you have a rod right here, a plastic rod, and on both these objects are in charge. You have like a cloth, like presumably like silk. You rub them together. Well, the protons and the electrons and the protons and the electrons of both of these objects will go really close to another because they're rubbing on each other. So one of the objects will start to grab electrons from the other object. Will start to grab because they're so close that some of the protons, they don't move, but they start snatching electrons from the other object. And this snatching of the electrons will create an imbalance of charge, because over here, since the cloth snatched the electrons, it has more electrons, more negative charges, more negative electrons than protons, so it will become negatively charged. And this will become positively charged, not because like protons moved, but because it lost electrons. There are less electrons. That means the positive protons will win out, so it will have a net positive charge. So the next one we're going to talk about is charging by conduction or contact. So what happens if you have a charge that an object that's already negatively charged? Okay, so if you have an object that's negatively charged, then what you can do is you can touch it to an electrically neutral object, and the electrons, seeing some protons over here, some of them, well, I said some for a reason, there's still some protons over here, but some of the electrons will start flowing in here. And since this object is presumably neutral, having an equal number of protons and electrons, the electrons will win out and the object will become negatively charged. Okay, then induction, this method of charging, induction basically means when you have a negatively charged object, okay? So what happens over here? So you have a negatively charged object, and you could see the negatives being so close. Well, you might know that opposites attract and like charges repel. So the like charges, the electrons, they don't want to be near this electron rod. So the electrons will try to escape and go to the other side of the sphere or the object that you're looking at. Then all you do is connect it to what is known as a ground, a reservoir of charge that electrons just want to flow through. So it could be your finger, or it can be an actual wire connected to the ground. So anything that has a huge reservoir of charge. So this, or like a wall. So this will draw the electrons away, and this will leave you with a positive charge. So now we're going to talk about electric force. Okay. So electric force, the basic equation for electric force is known as Coulomb's law. And you can see where we got the unit Coulomb from, Coulomb's law. Coulomb's law gives the formula for the electric force between two charged particles. Now, in this equation, you should only substitute the magnitude of the charges. Don't put the negative sign because it's negative, because for direction, you just look at the signs of the charges. Opposites attract and like charges repel. So you have a negative and a negative, then the forces will cause them to pull apart rather than push them together. And so the magnitude of the electric force is given by this equation, where Q is the charge in coulombs, R is a distance in meters, Fe is the electric force in newtons, and Ke is a constant known as Coulomb's constant. which has a value about 8.99 times 10 to the 9 Newton meters squared over Coulomb squared, which you can just approximate as 9 times 10 to the 9 Newton meters squared per Coulomb squared. So I'll use this 8.99. It's the value used in many sources, and it's a bit more exact, so I prefer that. But you can use 9. 9 is probably like a good value for KE. So here's a practice problem. And before we start this practice problem, notice this equation looks similar in a way. It might be creeping back to you that this equation looks a lot like law using universal gravitation. It's true. And Q1, Q2 are basically M1 and M2 in the gravitation equation. So the charge is basically substituted for the mass. These are both forces over here. K, there's always some constant. For the electric force, it's Ke. For gravitational force is big G. Then you have R squared, and both of them are inversely proportional to R squared. So you can obviously notice this similarity over here. So let's actually start a practice problem. An electron, and I'll give you the masses here again, and the charge is placed 3 micrometers. If you don't remember from microcoulomb, 1 micrometer and micro anything is 10 to negative 6 meters, so a millionth of a meter, from a negative 20 nanocoulomb. So nano is, didn't put that there, but nano is a billionth, so 10 to negative 9. So negative 20 nanocoulomb charge. So part A, how many excess electrons make up the negative 20 nanocoulomb charge? Part B, what is the acceleration of the electron at that point? So the number of electrons, okay, the number of electrons will be negative 20 nanocoulombs. So divide by negative 1.6 times 10 to negative 19 coulombs. Why did I do that? Because you have all these charges, all these electrons, and you have an excess number of electrons because this is a negative charge. So if you have these excess electrons creating with this charge, so if you multiply this charge times some number of electrons to give you an excess amount of this charge, then you could easily use some algebra and divide by this number, negative 1.6 times 10 to negative 19 coulombs per electron. And you get about 1.25 times 10 to the 11 electrons. So it's a massive number of electrons, even for a small charge. Then you can just substitute Coulomb's law equation over here, Ke, Q1 times Q1, Q2 over R squared. You can substitute these values. Ke is your constant, Coulomb's constant. Your charges, Q1, Q2, or Q1 is your negative 20 nanocoulombs, the 20 times 10 to negative 9 coulombs. And this is your electron charge. Notice we didn't put any signs here because the direction is determined by the sign. So they'll both repel. You have negative and negative. So like charges repel. Okay, and you divide that over the distance squared. So 3 times 10 to negative 6 meters squared. And you get about 3.196 times 10 to negative 6 newtons. But that's only the force. If you want to find the acceleration, what you should do is you should just use Newton's second law. The acceleration equals net force over mass. So we already find the net force over here. And you might have noticed we didn't put gravity, but our next example will tell you exactly why. So since this is our net force, and you divide by the electron mass, which I give you over here, so you substitute that in, you get 3.51 times 10 to the 24th meters per second squared. So that's a massive acceleration. Why? And because the charge imbalance and the electric force itself is really strong due to this little constant right here being huge. So You might realize, why aren't then objects, just so many objects, charged if charge is just an inherent property? It's because of this acceleration over here. If you have positive and you have negative coming together, they'll just stick in like billionths and trillionths of a second. So many objects you'll find will be electrically neutral because protons and electrons just attract each other so fast. So here's a next practice problem, and here's why we ignored the gravitational force. So you have a proton and an electron are spaced 3 femtometers, where 1 femtometer is 10 to negative 15 meters, apart. Find the ratio of the electric force to the gravitational attraction. So if you don't know what that means, if you were to divide the electric force by the gravitational force, what will that number be? It will be an actual number because newtons divided by newtons will cancel out. So this will be a number. So what you do, Fe divided by Fg. So you have Ke Q1 Q2 over R squared divided by G M1 M2 over R squared. And since these are both the same distances, and we're going to assume them to be in the same place for this calculation, R squared can cancel out. R squared, if you multiply this by the reciprocal of GM1, M2 over R squared, you see that the R squares will cancel out and you'll be left with this expression, KEQ1, Q2 over GM1, M2. So you have FT divided by FT equals all these numbers. So if you remember, big G is this number over here, okay? And if you substitute all these numbers in, you get this. Fe divided by Fg equals 2.270 times 10 to the 39. So this is a huge number, and but this is actually a extremely large number. So the meaning of this number, that's how many times larger the electric force is over this distance, well, actually over any distance because the R squared cancels out. That's how many times larger the electric force is than the gravitational force for a proton and electron. Okay, it's different for particles, but why? Because the charge number, the magnitude of the charge is much larger than the magnitude of the masses. So if the masses were larger and they were actually countable masses, like the mass of a small rubber ball, then you can't really ignore the gravitational force. However, when it's something with such small masses and such large, well, compared to the masses, charges, then this number is going to be huge and you just neglect the gravitational force. So now we're going to explore a new concept known as the electric field. The electric field is a region of space around a charge that is affected by a charge. This field delivers the electric force to the other charge, to other charges. Okay, so you might have already noticed you have proton, you have electron, and then they miraculously just stick together. But they're not touching. So if they're not touching, what is delivering the force? What is delivering the force? Like when you push a book, your hand is the one actually exerting the force on the book. So what is exerting the force on the electron from the proton? Well, it's this notion of an electric field. Okay? And since it's a region of space, we can give like a 2D approximation using electric field lines. So if you want to draw these lines must start on a positive charge and go toward a negative charge. And the electric field lines cannot cross. And number 3, the direction is found out by the force on a positive test charge. Basically means the electrons, a negative charge will feel a force opposite the direction of the electric field because the direction is found out by the force on a positive charge. So these are some examples. You have your basic, just positive charge right here, single positive charge. The electric field will just span outward, okay? But be careful, this is not just in one plane. This is a whole region of space. Think of it as like a sphere around the one little charge. and it's like gradually like spreading out the sphere. So that's what these lines represent. It's a 2D approximation of a 3D concept. So these lines will spread outward from the positive charge. They always must start on a positive charge. And for negative charge, it'll go inward because they must end on a negative charge. So it will go inward. So here's how you could just use these lines to help you figure out stuff about electric fields. So let's look at diagram number 1, okay? So pretend this red dot over here, which I'm using as a pointer, is a positive test charge. So over here, it would feel a force like this. It would feel a force pointing that way. Over here. Okay? Then it will start to get attracted to negative. So that's why these directions come here. You just place all these positive test charges and just find out where the force is getting directed towards. And you'll get this cool looking pattern over here. And you could also use these lines to find out the strength of the forces. So if you have a lot of lines in one place, say over here, or actually near any one of the charges, if there are a lot of lines in that particular area, okay, there are lots of lines, that means the force is strong there. The force is particularly strong there rather than out here. Because, you know, from Coulomb's law, it's a larger distance away, so the force will be less. And it's shown by these lines that the force will be less because there's only one line in this little region rather than over here there are like six lines over here. Same thing over here. You have a lot of lines here, so you'll experience a strong force over here and a strong force over here, but not as many lines over here. And there's actually no lines over here. The lines don't ever go here. If you actually add up the net force on a positive charge up here, the right one wants to push it to the left, doesn't want positive charge on its territory. And same thing for the left charge. It will push it to the right. And assuming that both of these have the same charge, the forces will cancel out if you put it straight in the middle. So the forces will cancel out and it'll be left with 0 net force. So the charge will just stay there. There'll be no force. That's why you see a complete absence of electric field lines over here. And since electric field lines are determined by the force on a positive test charge, the lines can never cross. Why? Because if the lines did cross at some point, like over here, at some random point, then if they crossed, it would be experiencing a force in 2 different directions at once. Okay, and that cannot be a net force. The lines tell the direction of the net force on a positive test charge, not the directions of the individual forces. So net force can only have one direction. So that's why the lines can never cross. And as you can see here, the lines just will never touch, but will start to go up and down, trying to look desperately for a negative charge to end on, because these don't ever end on positive charges. So it will spread upward and downward over here to find a negative charge to end on. So they don't give you the signs of the charges right here, but we can easily find the signs of the charges. This charge, well, the lines are coming out of it, so this will be positive, and it will start to go towards this little charge, so this will be a negative charge. Now, if I were to ask you the question, which object has more charge, it would be this one. Why? Well, it's easy to find out. There are way, way more lines coming from this charge than ending on this charge. Okay? way more lines just emitting from this charge. So that means the force will be greater here. That means the charge must be greater here because you're using the same positive test charge for all of these for it to find the magnitude. So this will have a much larger charge, and this will have has less magnitude of charge than this one because there are not as many lines coming here. And same rule applies. So never touch, and starts on positive, ends on negative, and direction is determined by the net force on a positive test charge. And there are two equations that can be used to find the electric field. This one equals Fe over Q and equals Keq over R squared. So our E is the electric field in newtons per coulomb. So that's its own unit, newtons per coulomb. Fe is your electric force in newtons, and Q is the charge in the field, little q. You see I have a little q and a big Q. The little q is the charge in the field. It's the charge, your positive test charge. And big Q is the charge generating the field. And Q, you can use a little algebra to derive actually this equation over here. So just substitute Coulomb's law over here. And the Q's will cancel out, and you'll be left with this. So you have Q, big Q is the charge generating the field. R is, of course, your distance. And Ke, again, is Coulomb's constant. I put the value right over here. And if you look at this, the electric field defined is just a force per unit charge. So if you were to have an electric field of 5 newtons per coulomb, that means every coulomb of charge you put there, you'll have a force of 5 more newtons. So it's just force per unit charge, right? The unit is 1 coulomb. So here's just a practice problem over here. So 2 charges, Q1, which is 3 nanocoulombs. Again, nano is a billionth and of a coulomb, so 10 to the negative 9. And Q2 is negative 50 nanocoulombs, are separated by 0.3 meters. The Q2 charge feels a force of 1.50 times 10 to the negative 9, negative 5 newtons to the right. Find the electric field at that location. Okay, so what you can do here is you can basically use both equations. E equals Fe over Q and equals Keq over R squared. So the easier choice, of course, if they actually give you the force on the charge Q2, would just be to substitute the values into this equation. So you have 1.50 times 10 to the negative 5 newtons divided by negative 5. Well, yeah, you could just put the magnitudes over here. Always put the magnitudes over here. And that equals 300 newtons per coulomb. And the electric field could also be determined by using this equation. And use the charge generating the field since you have big Q over here. And you'll get 299.67 newtons per coulomb. And these results are just slightly different. Why? Because these results are slightly different. Why? Because this constant is an estimate. It's rounded. So if you actually use the exact value, you will get 300 newtons per coulomb. So they will be the same regardless of which equation you use. Just the results being slightly different because we use rounded numbers for Ke. Okay, so here's another practice problem. Suppose you had a charged sphere with mass 20 grams hung by a cord. A constant electric field of magnitude 30,000 newtons per coulomb is directed rightward and moves the charged sphere until it makes an angle of 15 degrees with the vertical. So find, part A, the tension in the cord, and part B, the charge on the sphere. Okay, so you cannot really neglect gravity as we did with all these charges, with these, because these are little point charges, they're little points. But this is like a full mass, and this mass is not small, it's big. Well, big by like an actual countable, measurable mass. So by actual, like a normal physics lab, you could use a balance to measure this mass. So it's measurable, so gravity cannot really be ignored. So what you want to do is you do is Fg equals mg, so 0.02 kilograms times 9.81 meters per second squared equals 0.196 newtons. Okay, so turn on my little draw tool right here. So I found mg over here. mg over here. And so what I can do is if I want to find the tension, and remember from forces, you could break this tension force up into little components. Ty, and Tx. And this is your angle over here, because this line and this line are parallel, so you can use alternate interior angles. So this will be your angle, and they use theta. So this is Ty, this is Tx. So if you know mg, and this is an equilibrium, so this is an equilibrium. So what you can do is you can find Ty over here. So Ty will basically equal mg. So that's basically what I did over here. And so Ty is over here. So T cosine theta, because the angle's right next to Ty, equals Fg. And you could just do T equals Fg divided by cosine theta, substitute in the values. 0.196 newtons divided by cosine of 15, and you get 0.203 newtons. Okay, so if we want to find Tx, so you already know tension right over here. Okay, I'm not going to bother drawing the y components. We're done with that. So if you want to find Tx, well, since this is an equilibrium, there must be something balancing out the Tx, and that is the electric force, Fe. So Tx must equal Fe in order for the object to be in equilibrium. Otherwise, it would have like accelerated. So if Tx is equal to Fe, and we said that this is our angle, that means Tx is just the sine of the angle. So tension times the sine of the angle. You can just draw a triangle to prove that. So this will be the sine of the angle. So Tx equals Fe, which equals Qe. You can just solve for Fe equals Fe over Q. Solve for Fe, so you get Qe. So you have Tx equals Qe. So as I said, T sine theta, so Tx is basically T sine theta equals Qe. Then you could divide by E to solve for Q. Substitute in the values, 0.203 newtons, the tension force we found over here, times the sine of 15, divided by 3 times 10 to the 4th newtons per coulomb. And you get this value, 1.752 times 10 to the negative 6 coulombs, or 1.752 microcoulombs. So now we're going to delve in electric potential energy. So just a quick review of energy. So work is the force causing the displacement. So it's a change in energy. And potential energy is stored energy, energy based on position. And I put the work formula in case you don't remember. So suppose we have two parallel plates. So one thing to know about parallel plates is that they have a constant electric field. So it's why we use parallel plates for our examples over here for simplicity. And because they will be under test, only parallel plates. So let's say positive charge moves from point R to point Q, then to point P, then back to point Q, and then release. So you do that process. So when the charge moves from R to Q, from over here, you have to do some work on the charge to move it. So because the electric field will oppose you. Okay, because the charge is positive. Positive, that means the positives over here just want to push it back, and the negative one here, negatives over here wants to grab it in. So the field will oppose you. So you will feel some opposition, so you have to do some extra work on the charge to move it. Since the field will oppose you, that means you're transferring energy to the charge. So while doing work, because work is simply a transfer of energy. So if you transfer energy, the charge will get some energy, some extra energy from you doing the work on the charge. And this is known as electric potential energy. Okay? So if you move the charge from Q to P, so I should have put that there, might confuse you, but I forgot to put that there. So if you move it from point Q to point P, okay, then the field will do no work on the charge because the force and the displacement are perpendicular. Okay, just use my draw tool. So you're moving it this way, and the electric field, remember, the direction of the force will be the same direction of the field because the charge is positive. Then these are perpendicular if you move it horizontally. So if you remember from FT cosine theta, the cosine of 90 is 0. So there'll be no work done. That means you're neither adding energy or removing energy. So you're not really do work as you move from Q to P. Or like the field will not do work. You will do work, you're applying like a force, but the field will not do any work. And the same if you move it back to point Q. Okay. So if you move it back to point Q, then the field will not do work. And if you release it, the field will do work. And it will start losing energy. The energy already put there will lose energy and it'll gain kinetic energy as the field starts to do more and more work on the charge. It will gain kinetic energy as it moves more and more towards its negative. Okay, and another thing we're going to talk about is electric potential. So just as electric field, we said, is the force per unit charge, electric potential is a property of space, and it's the electric potential energy per unit charge, and is measured in joules per coulomb or volts. Okay? And electric potential is a property of space. Okay? So over here, every point on this line here will have a potential of 75 volts. Okay, 75 volts of potential, and will not change as long as you're in this line. However, if you go here, you'll have 50 volts, 25 volts, 0 volts, and 100 volts. So the potential changes depending on space, just like the electric field. Okay? So it's just the energy per unit charge. So, okay, so these are the equations you need to know for the test. They're incredibly simple. Okay, so you have your change in potential energy will be, since the electric potential is the energy per unit charge, so energy per charge, then you could just rearrange this here. So the change in potential energy, so the energy gained or lost will be your charge Q times the change in potential, so the potential difference. And you could derive this thing over here as delta V equals ED. You can substitute that right over here to get QED. Okay, so you might wonder how we just pulled out of all of these equations out of thin air. Okay, so we know that the change in potential energy, or just potential energy in general, per charge Q will be your potential difference, or just the potential. Okay, so you know that. And the change in potential energy will also be the work done. If you're changing energy, so by conservation of energy, there must be some work done on the object. So there must be some work done on the object. Will just be FD. So we'll neglect the cosine theta for now. So we'll assume it's parallel to the displacement, or in the same direction as the displacement. Okay, so the force on the charge that you have to apply to at least get it moving at a constant velocity, that'll be the force exerted by the field. So that'll be QE. So QE, because E equals F over Q, so QE times T. So that's where we get this from, this relationship. And we know that the potential is equal, and this are equal. That means if you divide both sides by Q, you get this. Oh, sorry. So you get this relationship right here. So you get the third relationship. So just if you want to wonder where we got these equations from. Okay, so here's a practice problem. It's a long one. So an electron is accelerated through a potential difference of 2,000 volts, then heads into a set of 0.2 meter long parallel plates, 0.3 meters apart, with a potential difference of 3,000 volts. Find the electric field between the second set of plates. Find V naught. So V naught is the velocity right before it enters the second set of plates. And find the electron's velocity the instant it leaves the second set of plates, V1, magnitude and direction. So the angle with the horizontal, so direction and the actual speed. Okay. So if you want to find the electric field in the second set of plates, I give you the potentials over here, 3,000 volts. You use delta V equals ED. So E equals delta V over D, so 3,000 volts. Divided by 0.3 meters, the actual distance between two plates. So divide by 0.3 meters equals 10,000 volts per meter. So volts per meter is just another version of electric field. So volts per meter is the same as newtons per coulomb if you actually do all the dimension work. So this is another unit for electric field, and you could use the change in potential energy. So the potential energy in this case lost into kinetic energy equals Q delta V, and you could just put the change in potential energy equals the kinetic energy mv squared over 2, or 1/2 mv squared. And if you substitute in over here, Q delta V equals mv squared over 2, and then solve for V, you get this expression over here, square root 2qv over m, and you could substitute the values given over here, take the square root, just remember that, and you get 2.65 times 10 to the 7th meters per second. Okay, so that's the velocity over here. Okay, so the positives, we'll start to pull it up over here. And the force will be opposite the direction of the field because the charge is negative. So start to get pulled upward. So we're going to define upward as positive, downward as negative. So F equals QE. So the magnitude of the force will be QE, which is 1.6 times 10 to the negative 19 coulombs, times the electric field we found in this part, 10,000 volts per meter. And we get 1.6 times 10 to the negative 15 newtons. So that's the force the electron experiences while over here. And, forget this diagram. This diagram's wrong. The arrow is supposed to be facing rightward rather than leftward. So in case that bothered you. But anyway, moving onward. Or actually, the arrows shouldn't be actually changed, but the signs should be changed. So the left side should be negative, right side should be positive, just in case you were bothered by that. Okay, so onward, acceleration equals net force over mass, the second law. You can substitute in the electron mass will be given to you on the test, and I gave it to you several times on the presentation. So no need to memorize the numbers. And you get 1.756 times 10 to the 15 meters per second squared upward. So the electron will start to bend upward. So delta x equals Vx delta t. So it is basically a kinematics problem. So how long will it take for the electron to travel this distance? So we want to find the velocity over here right after it leaves the plate. So we want to find the time it takes for the electron to actually get to the end of the plates. So the x component will stay constant because there's no acceleration being experienced. So we could use this equation over here. So basically the definition of velocity. And you can solve for delta t. And if you substitute in the numbers, you get 7.55 times 10 to the negative 9 seconds, or 7.55 nanoseconds. Okay, so Vfy, so I'm going to use Vy equals V naught plus A delta t, or AT. Okay. And V naught y is 0, so that part is gone. It's 0, it's launched horizontally. So we got Vfy equals A delta t. And if you substitute in the numbers, you get 1.32 times 10 to the 7 meters per second. But we only found the components. You already know the components. But if you want to find the direction, you can use the Pythagorean theorem. And so Vx squared plus Vy squared equals V squared, where V is the total velocity. And square root and substitute the numbers. So that's 2.65 times 10 to the 7 meters per second. And that square that. And then 1.324 times 10 to the 7 meters per second. Square that number as well. And take the square root of the sum. And you get 2.96 times 10 to the 7th meters per second. Okay, so that's the total magnitude of this velocity v1. So we'll be going this fast. The direction is easy to find. You can find the tangent of the angle by breaking up the velocity into components, which you probably should have done. Then if you find the tangent, I use tangent because this velocity magnitude is even more of an approximation because we took the square root and because we use approximations of these. So we're going to use the actual y and x components, use tangent. So you get the inverse tangent of Vy over Vx, substitute in the values, and you get an angle 26.5 degrees above the horizontal. So we found the magnitude and direction of V1. So it was a taxing problem. It was a problem you got on the sheet. But if you actually remember how the concept, and this is the importance of actually remembering the concept you learn in each of the units. If you remember the concept, then stuff like this shouldn't be that difficult for you, and you can apply these concepts to solve a problem like this. Okay, so let's move on to the part that is actually important. Circuits. So a circuit is a closed path in which charge can flow. So the source for this movement is the electric potential difference created by the battery. Okay? So here's some examples of some circuits. So a diagram at the top shows a series circuit. Okay? The bulbs are connected in line, and there's one pathway charge can take through both components. Okay, so you see the actual, how the circuit will look like, and you see this thing. This thing is a circuit diagram. So light bulbs are usually represented by this, although you could have a little zigzag surrounded by a circle. So that's also another symbol for light bulbs. because circuit diagrams can look different from person to person, so these symbols are like the international standard for drawing circuits and actually like representing circuits so that other people can use them and find out exactly what you're trying to say in the circuit. So as you can see, charge will get forced through this potential difference, gain some, and it will flow through here, go through these light bulbs, and there's only one pathway for the charge to flow. That is this pathway, and it will go back again through the battery, gain potential, and then will flow through again, okay? So parallel circuits are shown in the bottom diagram, okay? These circuits have junctions. So this is a junction, and this is a junction where the flow of charge splits up. Okay, so here's a circuit diagram for this. So your total charge will come here. So all the charge will come here. And at this junction over here will split up. Some of the charge will flow through this light bulb, and some of the charge will flow through this light bulb, and it will just keep on flowing through the light bulbs until it meets at this junction. So this charge will go over here at this junction, and this charge will go at this junction, and they will meet up again to form this flow of charge and goes through the battery. So it will split up at the junction. Okay? So might have said so the flow of charge is defined by quantity which we call electric current. So current is the flow of charge and is defined by the charge that moves through a given point in a given amount of time. So they're measured in units of coulombs per second or amperes. So here's a definition of current. We use the letter I for current. So I equals delta Q, so the amount of charge divided by delta T, the actual time it takes. So Q over delta T or delta Q over delta T. Okay, so the actual amount of charge that flows through a point in a given amount of time, delta T. So that's current. And current's measured by amperes. If you don't notice here. So here's a practice problem, just a quick one. A battery charger charges a battery with a constant current of 3.25 amperes for 3 hours. So please find part A, the charge accumulated on the battery, and B, the number of electrons that were transferred in the charging process. Okay, so you just use I equals delta Q over delta T. So we're given I, we're given delta T. So if you want to find Q, you could use this equation, but first you have to convert delta T into seconds. Seconds is the actual SI unit, not hours. We're given hours. So you could just use 3,600 seconds per hour, or you can convert from hours to minutes and then convert from minutes to seconds. Either way, you get 10,800 seconds. So that's how long in seconds the battery was in the charger. Then you could use I equals Q over delta T. So you can multiply both sides by delta T and substitute the numbers. So you have delta Q equals I delta T equals 3.25 amps times 10,800 seconds. That equals 35,100 coulombs. Okay, so Ne, so you just use that to, and the number of electrons. So Ne equals Q divided by QE. QE, so one electron will have charge of QE. So if you want to find the number of electrons that makes up this charge of 35,100 coulombs, then you just divide by the charge on an electron. Again, you'll be given this number over here. You don't need to memorize it. And you get 2.194 times 10 to the 23 electrons. So that's the number of electrons that were transferred in this charging process. So a massive number of electrons. So next we're going to talk about another concept known as resistance. So resistance is the opposition to the flow of charge or current. Resistance depends on the length of the object, the thickness of the object, and the actual material that the object is made out of. And this is measured in units of ohms. So the ohms, and this is the symbol for ohms, the capital letter omega. So the actual resistance of an object, okay, is measured by R equals this letter rho times L, the length divided by A. And this rho is the resistivity. And the resistivity is determined by the actual material itself. So whether the atoms actually are bunched up or like spread out, and if the actual properties of the material will allow electrons to pass through the material easily. So this will give you the resistance, remember, and resistivity, as you can see, is given in units of ohm meters. You have your length in meters, and A equals the cross-sectional area equals meters squared. And cross-sectional area, if you don't know what cross-sectional area means, okay, so if you have a little wire over here, okay, and you chop it in half, okay, this area over here and this area, the cross-sectional area, so that's the A you put in here. You don't put the surface area, you don't put the area of any other side, but the area that the electrons will actually pass through. Okay, and you can actually see that this equation kind of makes sense. If the length is bigger, then it'll take a longer time for electrons to pass through, more resistance because it's a longer path, and its resistance is inversely proportional to area, because as area gets larger, resistance gets smaller because there's more space for electrons to flow through. However, if area gets smaller, then resistance gets larger because the electrons are all squeezed up and have to bunch through. Okay. So let's have a quick practice problem. So let's say you have a cylindrical copper wire with a radius 2.31 times 10 to the negative 2 meters and length 1.4 meters. Okay, what is the resistance of the wire? So the resistivity of copper is 1.72 times 10 to the negative 8 ohm meters. And you can just see right here that copper is conductive, so that's a very low resistivity, 10 to the negative 8, so that's quite low. And I give it a radius, so if you want to find the area, R equals PL over A, and we know that A equals pi r squared, so it's basically area of a circle. The electrons will be going through the circular part of the wire. And so they'll not be going through the sides of the wire, but rather be going through the circular part of the wire. So you use the area of the circle formed, and you get R equals rho L over pi r squared. You substitute in the numbers, okay? And then you get this amount at 1.45 times 10 to the negative 5 ohms. So very small resistance. Very, very small. But, so only if you're doing very delicate experiments will this resistance actually affect you. So now we're going to learn about Ohm's law. Ohm's law states that the voltage across a component in a circuit is directly proportional to the current through the component and its resistance. In equation form, this is V equals IR, delta V equals IR. For delta V is the voltage in volts, I equals the current in amperes, and R is the resistance in ohms. Okay, so and if one more thing, delta V, the voltage, well, in a circuit like this, you can just use the voltage of battery, but what this delta V really means is the voltage drop across the component. And this definition of voltage across the component will be especially important as we get into analyzing more and more complicated circuits. But let's start with this example. So find the current running through the 3 kilo ohm resistor. So kilo is 1,000, so 3,000 ohms. Okay, so you have delta V equals IR, so you can solve for I, and I equals delta V over R equals 9 volts divided by 3 times 10 to the 3 ohms, or 3,000 ohms, and you get 0.003 amperes or 3 milliamperes. So either of these could work, so I just changed the unit, the prefix over here, added milli, so either of these two answers can work. Okay, why does we can just use battery voltage? Because it just loses some voltage over here, and then it will gain again. So the voltage drop over here will be 9 volts. Because all the voltage must be dropped over here. Okay? Because if all of it weren't, okay, then you have a little voltage left. It'll gain 9 volts and it'll start getting energy out of nowhere. Because voltage is basically the potential, and potential is basically the energy per unit charge. So now we're going to start getting into some advanced circuit stuff. So we're going to learn the loop rule and the junction rule. So these are two rules and laws that apply for all circuits, and basically you derive these and explain these using conservation of charge and conservation of energy. The two laws are these. So the junction rule, the sum of the currents in each of the branches coming from a junction must be equal to the current equaling the junction. So current in must equal the current out. The sum of the current in equals current out. So when a current, I'm going to use my drawing tool. Okay. So suppose you had a branch like this. So this is current I. Again, we use I for current. Okay, and it'll split at this junction over here. Split here. So you have I1 and I2. I1 and I2. Okay, I1 and I2. Then the sum of I1 plus I2, basically from common sense and from conservation of charge, you can't really lose some current or gain current, so I1 plus I2 must equal the original current I. So that's basically the junction rule. And the loop rule, so for any closed loop in the circuit, the sum of the voltage rises and drops must equal 0. And voltage drops across are the same across all components in parallel. Okay? So if we have little resistors, okay, 2 resistors and 2 batteries, okay, 2 batteries, well then the charge will gain some voltage over here. So the charge will gain some potential over here, gain over here, okay? But then it will lose some over here and it'll lose some over here. However, the rises and drops must equal 0. So the voltage rises equals the voltage drops. Okay? Why? Because again, I think I may have explained this in the last example. If, let's say, the voltage drop was if it lose more voltage than it gained voltage, that means you must have had some extra energy there somewhere. And since there's not really any work being done, you just violated the conservation of energy. Okay? But what if it didn't drop enough voltage? Okay? So the voltage rise was actually greater than the voltage drop. That means it lost energy somewhere, okay? It lost some potential somewhere. And potential is basically energy per unit charge. So it lost potential somewhere. And that means you lost energy and there's not really work being done on the charge, on the electrons. That means you just violated conservation of energy again. So the loop rule, the voltage rise must equal voltage drop. And the voltage drops are the same across all components in parallel. Okay, so you had resistors over here, another resistor over here. So that's a battery, another resistor over here. Okay, and that means the voltage drop, it will lose the same amount of potential in this resistor and so the voltage drop, the potential it loses in this resistor must equal the potential it loses across this resistor. And this fact will be especially helpful when we start solving some complicated circuits. So now we're going to talk about resistors in series and parallel. So when there are multiple resistors, using Ohm's law once will not work. So this example we did over here, you just used Ohm's law once, but that was only because there's one resistor. When there are multiple resistors, you have to find the total resistance, the equivalent resistance, Req. And the equations are this, the top one's in series and the bottom one's in parallel. So do not confuse these. So our equivalent resistance, the total resistance equals R1 plus R2 plus all the way to Rn. So this works, that basically means this works for any amount of resistors in parallel. So you can have 1,000,000 resistors in, sorry, this one's for series. So 1,000,000 resistors in series, I think I said parallel. So 1,000,000 resistors in series, and as long as they're all in series, you can use this formula, add up all the individual resistances, and you will get the total resistance. And same, well, sort of the same for parallel, the same concept. This can work for 1,000,000 resistors in parallel, and as long as they all are in parallel, that means that you can substitute all the individual resistances. And I get 1 over this equals 1 over this plus 1 over this plus 1 over this, and all the way to 1 over the last one. So n amount of resistors. And what some people might do some of the times is they add up all this stuff and then they pass that off as the equivalent resistance. But that's not right. You have to take the reciprocal of that, the sum over here, so you can actually get the equivalent resistance. So here's a practice problem. So find the equivalent resistance of the resistors, okay? Might seem daunting. You have series or parallel, you have all these different things. But what you can do is, and the equation, just if you want to know, you can derive these using the loop rule and the junction rule. But back to the problem, you have to combine, start in specific branches and work outward so you can get the total equivalent resistance. So what you should do first, we'll simplify these two, okay? So obviously you can see they're in parallel because, well, they look parallel. So you have 1 over R1 plus 1 over R2 equals 1 over 9 ohms plus 1 over 8 ohms equals 0.236, well, inverse ohms, that's the actual unit because you're basically taking 1 over ohm. And also it gives you a reminder that you have to take reciprocal as well. So I use that unit. So if you want to use it, knock yourself out. But just remember, you have to take the reciprocal of this number. And you get the equivalent resistance of that combination as 4.235 ohms. And keep in mind that this is only for these two. So we just found the equivalent resistance for this. Okay? For this. Okay, so you can replace that with 4.235 ohms. Okay? So what you can do afterward is, you see it doesn't split here anymore. So this resistor over here, this one, so this one and this one are in series. So you can add them together using the series formula. So you have another equivalent resistance equals R1 plus R2 equals 4 ohms plus 6 ohms equals 10 ohms, okay? So you add them up together, you get 10 ohms. So this combination will be 10 ohms. Okay, so just pay attention to the red resistors. So those are equivalent resistors. This is 10. And this is 4.235. 4.235 and 10. So I'm going to just cross through just to make sure you don't look at those resistors. So we're done with those. So you have 10 ohms and you have 4.235 ohms and they're in parallel. So we can combine those together. So we can combine those together and you get 1 over the third equivalent resistance equals 1 over R1 plus 1 over R2 equals, and that equals, if you substitute in all the values, 0.336 inverse ohms. Again, just a unit, and you get the third equivalent resistance calculation to be 2.975 ohms. So cancel, cancel, cancel. Okay, I'm just going to redraw the diagram. And it helps to redraw the diagram. I just don't have that much space for so many like redrawings. So I'm just going to redraw it right now because it's evidently very messy. So you have B, A, this is 20, this is 3, and we just found this one as 2.975. And imagine that as if you were current, okay? So current would split through here, okay? It would split here. So you can't really add the 20 and 3 ohm resistors together because it's a junction. So actually this whole combination and this will be in parallel. So what you should do here is these two, the same current will be flowing through this one, this resistor, and this resistor. That means these two are in series. So if you want to use the parallel one, you have to simplify everything first. Because these only work for the individual resistances. So you can't put 1 over 3 plus 1 over 2.975 plus 1 over 20. So you have to put the simplified version. So you use your fourth equivalent resistance calculation. Okay, so R1 plus R2, substitute in the values, and you get 5.975 ohms. And now you can use the parallel formula. So you have 1 over the fifth equivalent resistance calculation equals 1 over R1 plus 1 over R2 equals 1 over 20 ohms plus 1 over 5.975 ohms equals 0.217 inverse ohms. Then take the reciprocal, you get 4.601 ohms. So that's the equivalent resistance of this entire combination. That means the circuit will behave exactly the same if you just put a resistor of this resistance. So it's quite involved, but basically you simplify everything first before doing anything else. So start from the inside over here and work your way out by simplifying and then using the formulas. And then you would, until you get to the very last calculation and you get 1 resistor, and that'll be your total equivalent resistance. Whew, long unit. Okay, so now we're going to actually start solving circuits and actually finding actual values for circuits. So if you want to solve a circuit, well, first condense all the resistors in the equivalent resistor. Number 2, use Ohm's law to find the total current running through the equivalent resistor. Okay? And then part 3, work backwards. Use the loop rule and junction rule to find the current and voltage across each resistor. Remember, current stays the same across series because of the junction rule, and voltage is the same across parallel due to the loop rule. Because current, there's not really any junctions for it to pass, so the current must stay the same. So you can't really lose charge in the process. So those current stays the same in series, voltage is the same across components in parallel. So let's actually solve a circuit. Well, not really solve, but let's just find a value of the circuit. So find the current through the 250 ohm resistor. Okay. So first you find the equivalent resistance. So you first simplify these two. So these two are obviously in parallel. So you simplify 1 over 100 plus 1 over 250 equals this value. Take the inverse of that, take the reciprocal, and you get 71.4 ohms. So that's for this combination over here. Then you can use the same thing. Use parallel for these. Simplify this into one resistor. So 1 over 350 plus 1 over 200 equals 0.007 inverse ohms. And if you take the actual reciprocal, you get 127.27 ohms. So what you do is add these together. So 127.27 plus 71.4 ohms. That equals 198.67 ohms. So that's your total equivalent resistance over here of this combination. So find total current running through the circuit. Now you can use Ohm's law because now you condense it into one resistor, one equivalent resistor. So now you can use Ohm's law. Delta V equals IR. So you have I equals delta V over R equals 24 volts divided by 198.67 ohms. That equals 0.121 amperes. So this equals... Okay, so this equals, and this is 0.121 amperes. So that's your current. I'm just going to call it. So that's your total current. So that we already found was 0.121 amperes. So that's this current. But we want to find the current through the 250 ohm resistor. Okay? So what you want to do is you want to find the voltage drop across this combination. So you split it back up into 127.27 and 71.4 ohm resistors. Okay, then you you use Ohm's law to find the voltage drop. So you have 0.121 amperes times the equivalent resistance combination, 71.4 ohms equals 8.625 volts. So that's the voltage drop across the equivalent resistor. And if you break it up, since the voltage drop is the same across parallel components, the voltage drop across R1 over here and the voltage drop across R2 over here will also be 8.625 volts. Okay? So if you want to find the actual current through the 250 ohm resistor, you know the voltage, you know the resistance, and you also know the voltage drop, 8.625 volts. So substitute that in, and you get 0.035 amperes, or 35 milliamperes. Okay, so it's a complicated process, but it's not hard. You just put it in one resistor, find the total current, and then you break it apart and find like voltage drops or currents as you wish. So you can find the values you want. So you simplify and you start breaking it apart and use the loop rule and the junction rule. So next we're going to talk about ammeters and voltmeters. So ammeters and voltmeters are electrical devices used to measure current and voltage respectively. So ammeters must always be hooked up in series and voltmeters must always be hooked up in parallel. So this is because ammeters have near zero resistance and voltmeters have a huge resistance. So if you have current here, okay, if the ammeters have zero resistance, that means there'll not be a huge change in current, okay? So current will just flow through as if nothing was there. So it'll give you a precise measurement of how much current will be flowing through your component. However, if you connect the ammeter in parallel, since the ammeters have zero resistance, that means all the current will be drawn through the ammeter, and that much current will cause the ammeter to blow out. It's known as a short circuit. All the current will flow through the ammeter. It will cause it to burn out. So that's obviously not good, and it will not give you a good measurement. It will give you a seemingly huge current as your measurement. So always hook up ammeters in series. And the same thing for voltmeters. Voltmeters will have a huge resistance, okay? So since the voltmeter is a huge resistance, near none of the current will want to go through the voltmeter, okay? So the current will mostly go through here, giving you an accurate reading of the voltage drop across your component, okay? And voltmeters cannot be hooked in series, because if you want to find the voltage drop, you can't really find the voltage drop through a component. It has to be across 2 points, presumably before and after the component. And also, since voltmeters have huge resistances, none of the current will want to pass through that place, and you'll have a very, very awkward measurement, and you'll not get an accurate reading at all. So ammeters always hooked up in series, voltmeters always hooked up in parallel. Okay, so here's a practice problem, multiple choice. So which circuit connects the voltmeter and ammeter correctly? Well, the answer is circuit 4. Why? Well, circuit 1, you have an ammeter in parallel, so that's not good. Circuit 2, you have a voltmeter in series, so again, that's not good. Then 3, you have the ammeter in the wrong place. You want the ammeter to be measuring the current through the resistor, and you're basically placing the ammeter in parallel again. So circuit 4, you have the ammeter measuring the current through the resistor and the voltmeter across 2 points between, and with the resistor in between. So circuit 4 is the right choice. So next, we're going to talk about electrical power. So if you remember from work and energy, power is the rate at which work is done over time. So the power dissipated in a component is the product of the current through that component and the voltage across it. So you could use the electric potential equations and the definition of power to basically derive the electrical power is I times voltage, IV, or I delta V. Then you can use rearrangement and substitute Ohm's law to find different ways of expressing power depending on what you're given. So here's all the forms of power. Power equals I delta V equals I squared R if you just place delta V equals IR. Then you have delta V squared over R if you plug in delta V over R for I over here. So these are all the different forms of power, and they're all missing one variable. So it's very, very convenient to know these. And probably you won't be given these last two, so you can always derive them very quickly. Just put Ohm's law in for either voltage or current. So, practice problem, find the power dissipated in resistor R2. So you might be tempted to find the current through resistor R2, but that'll be a complete waste of time. Why? Because you know the voltage drop. You know the voltage drop across the R2 is the same as the one across R1, is the same across one across R3. So if you condense them into one resistor, they'll all have, that one resistor will have a voltage drop of 9 volts. That means all three of these resistors must have a voltage drop of 9 volts. So you know delta V, and you can substitute in this variation of power. Okay, so you have this delta V squared over R equals 9 volts squared divided by 2000 ohms equals 0.04 watts of power. Of power dissipated through that resistor. Okay, so here's the basically here's like the final test. Use the loop rule and the junction rule along with rules for parallel and series resistors to find the current through each resistor. After that, find the power dissipated in resistor R3 and the voltage drop across R4. So here's the solution. It's a pretty long solution. So first, condense into one resistor. Yeah, 1 over R23. So here's another way of writing equivalent resistors. R2, R3 condenses into R23. So 1 over R23 equals 1 over R2 plus 1 over R3. So that equals 1 over 30 ohms plus 1 over 50 ohms equals 0.053 inverse ohms. Take the reciprocal of that and you get 18.75 ohms. Okay, so actually finding the equivalent resistance is not hard. Okay, so it's a relatively simple circuit you've been given here. So if you want to find the total resistance R1, 2, 3, 4, that equals R1 plus R2, 3 plus R4. Because they're all in series. So 20 ohms plus 18.75 ohms, which is this equivalent resistance, plus 20 ohms equals 58.75 ohms. Okay, so now we got one resistor, which serves as the equivalent resistance for all of the resistors. So now we can use Ohm's law. So the Ohm's law you can use to find the total current, which is IT equals delta V over R1, 2, 3, 4, which is equal to 10 volts divided by 58.75 ohms equals 0.170 amperes. So if you're efficient, okay, you could find that R1 and R4 will have this current flowing through it because R1 is the first resistor to receive this current and is in series with the battery. So it will receive the current of 0.170 amperes. Well, it does split at this junction, but it also meets back before it goes to R4. So it will also receive the full current as well, 0.170 amperes. So we already found currents I1 and I4. Okay, so what you can do is if you want to find the potential difference, the voltage drop across R4, well, first you find the voltage drop across R1, so that's I1 times R1 equals 0.170 amperes. And notice, if you want to find this voltage drop, well, you can use Ohm's law, but only put the resistor R1. Do not put the total resistance. So put resistor R1, you get 3.40 volts. So that's the voltage drop across R1 alone, okay? Then you could do delta V 2,3, so the potential difference across resistor 2,3, so that little equivalent resistor. So you could do I23, so I23 in this, I'm just going to draw the diagram again because you might get confused. So I'm just drawing the diagram again. Okay, so this is 20. I'm not going to bother writing units in this drawing. So these are all in ohms. So this is 18.75 ohms. 18.75 ohms. And this is 20 ohms again. 20 ohms again. This is 10 volts. 10 volts. So if you want to find the voltage drop across 2,3, you find I23, which is the same as I1. So the I current going through this equivalent resistor, not the current going through R2 or R3, but the current going through the equivalent resistor I23 times R23, and you find the voltage drop across R23. So which is, if you substitute the values, you get 3.19 volts. Okay, and you can use the loop rule, or you could just use the Ohm's law again, but you should use the loop rule because I'm using the loop rule because it helps explain the loop rule more. So you're getting a gain in voltage from this battery. So there will be a voltage rise from the battery, and there'll be drops. So the voltage rise must equal the voltage drops. So the voltage rise, 10 volts must equal, we already found 3.40 volts across R1, 3.119 volts across R23, so we get 3.41 volts. So you subtract these and you get 3.41 volts across R4. And if you add all these up, you get 10 volts, satisfying the loop rule. So we already found one part of the problem. So we found the voltage drop across R4. So now we can find the current current in going through resistors R2 and R3. So I3 equals the voltage drop across R3 divided by R3. What's the voltage drop across R3? That's basically the voltage drop across R23 because it will split apart. So R3 will have the same voltage as R23 because R23 is an equivalent resistance. So that'll be 3.19 volts divided by 50 ohms, and you get 0.064 amperes. Okay? 0.064 amperes. So that's I3. So that's I3. And you could use the junction rule to find I2. Because I2 must equal I1. This is I1. Oh, I'm sorry. That looks terrible. Okay, so I1. And this is I2. So I2 must equal I1 minus I3. Because I1 equals I2 plus I3 from the junction rule. So you get 0.170 amperes minus 0.064 amperes equals 0.106 amperes. So we found the current going through all 4 resistors. So now the final part will be to find the power through resistor R3. You could just use I squared R or I delta V. We know all the parts now. So I'm just going to use I squared R, 0.064 amperes, square that, times 50 ohms, equals 0.204 watts. Okay, so 0.204 watts. So it's a long problem, but it's sort of complicated, but it's not hard if you have a firm understanding of the loop rule and the junction rule. Because the voltage drop in Ohm's law is only the voltage drop across the component. So you have to find the voltage drop across each component in order to find the voltage drop, the current through each component, which can enable you to find the power dissipated in each component. Okay, so let me turn my drawing screen off. Okay, so I think we're done. So this is probably the longest presentation we'll ever do. We just condensed electrostatics and circuits into one huge video. Okay, and it's good to know electrostatics, even if it was not on the test, because it helps you understand some of the concepts. However, this circuits part will definitely be on the test, so I hope you study hard, you get a firm understanding of circuits. And if you have any comments, just comment down. If you have any questions, just comment down below, and I'll see you in the next video. Bye-bye.